Good morning, everybody. I'm Tina Häggli from Snøhetta. Thank you for being here. I will now try for 15 minutes and shower you with slides and pictures, explaining you how the Snøhetta company will strive towards a zero-emission building society. We will start with a very short explanation of Snøhetta as a company. In the background here, in the environment, this is the Snøhetta mountain. The house in the foreground is the Norwegian Wild Reindeer Pavilion. It's an example of our normal interdisciplinary work between landscape architects, architects and interior architects. And it describes in the simplest way our efforts within architecture to bring these elements together. It's a 90 square meter pavilion, and it serves as an open public arena for a viewing point for both reindeers and for the mountain and for the environment. It's got one light bulb for lighting. It's got a heat source of fireplace. It's got robust and local materials. It sits up there in the mountain and actually just provides some comfort and a shelter for people who'd like to enjoy the environment. The main concept, the idea, is the contrast between the rigid outer shell, which is raw steel and wood, and the inside of an organic wooden structure, which is like eroded like rocks or ice in the mountains. And it's still produced in a very high-tech way by robotic strategies of how to carve out wood, transport it up there in 2 or 3 pieces and mount it in 1 week. So it's got some technology to it, even though it's as low-tech as possible. So that sort of explains the background of how we normally work. We're trying to get the most out of as little as possible. The next 2 projects I will show you have some added complexity to it. The complexity evolves around the aim to get energy use and emissions in our building industry radically down. The first example is a commercial building a little south of Oslo, which is a refurbishment, an office building. And the second example is a residential single-family house a little further south of Oslo as well, in Larvik. They will show different examples of strategies and different examples of architectural response. And both are pilot projects within the Zero Emission Building Center. I'm going to explain a little about the background for that center. The kind of complexity that's added to our architecture in these designs are coming out of the knowledge that our sustainable or unsustainable consumption in the building industry stands for 40% of the greenhouse gas emissions globally. Something drastically has got to be done, and out of these strategies, we are trying to get our buildings into zero energy and zero emission structures that will still serve the comfort of the people who are going to use it. SEB is a center. The Zero Emission Center is established in the university in Trondheim, Norwegian University for Technology and Science, and it's also containing more than 20 industrial partners who will collaborate with academia in getting to the solutions that we need to get our emissions and energy use down. The center has, among the partners, quite a few that wanted to move this all the way forwards to plus energy buildings and established this group called the Powerhouse. Snøhetta is among them. The good thing about these crowd of partners are that they actually are explaining the whole chain from the owner of the site, the developer of the building, and all the way down to the contractor. We're in it as architects. We have competence from the energy side. We have producers of facade elements. We also, even to the bottom here, the Zero, are an independent foundation striving for all industries in Norway to reduce their carbon emissions. So they are outside of the building industry and sort of operates as an independent voice also into politics. These partners needed some help to get around the definition of what is exactly a zero energy or a zero carbon building. There's so many different definitions out there. You have the passive house standard, you have the active house, you have net zero, you have near zero, you have ecological housing, and somehow we are not really we not always believe that all the products that are being presented as green are really green. We're starting to sort of question all of these facts around us. So the SEB Center helps the powerhouse to get into an understanding of what is really needed to do the efforts to bring your emissions and energy use down. You could read this as an ambition level where emissions from operational energy and the use of materials and the construction, and also in the end of life, are actually being compensated for with renewable energy on your site. No point in putting a windmill on the neighbor's site. You actually need to solve these within the task itself. This is, as you read it, just as the text, doesn't seem too complicated, but as the methodology of working, it's actually a totally different world than all other projects we ever tried. The really glorious thing about this really high ambition is that it forces it into a life cycle perspective, meaning that we will need to count for both the production phase of every component and material coming into our construction site, including the transport, the construction site itself, then the full operational time of 60 years, which is like the academic standard for how you count for things, is 60 years, is called the service lifespan. So all the energy used for your operation, and also the changing of components, all of those are going to be counted for. Even the demolition, we never got that far yet, but still, this is still to be developed as a way of counting and working. And all of that should be paid back with renewable energy production on your roof. So the first case, the first pilot started with Entra as a developer, had this complex of buildings a little south of Oslo. And they are actually quite general office buildings from the 80s. There's hundreds of these in Norway, probably around the world. We brought the energy use for those 2 blocks down from 220 kilowatt hours per square meter. I'm sorry, I cannot really immediately explain that in feet and BTUs and all of that, so you need to come up to me later if you need a thorough explanation of the measurements. But we brought it down to 19.7 without changing too much of the architectural aesthetics. Unfortunately, the municipality also wanted these to stay pretty much the same afterwards. They were very, very well renowned when they were there in the 80s, so they wanted them to, of course, look better, but still the same, still black, still box, still basically the same windows, nothing added on the roof. So that was the constraint that our office had to work a little with, but we got around it. And we focused on the inside. The inside of these offices were not at all to be the same as they used to be. These should come up to all standards, so daylight, acoustic strategies, indoor air quality. At the same time, provide spaces for different activities for people to feel creative, to have different work rhythms, and at the same time have a low embodied emission for all materials and a super low energy use. And that is, I'm now going to just show you a few examples or explain a few stories of how this group work turned into a circle. This is just an example of a circle. The team, of course, then were added a lot of people that we normally don't see around the table before, maybe quite close to the end of the project. We started sketching. People started measuring heat loss. We call them windows, they call them heat loss. How to measure those together. We found that most of the materials we preferred to use had really high emissions. We didn't really know what they contained. People from the SED Center came in with documentation, told us that we need to do some changes. Because all the time we need to measure back to how much roof area do we have to pay these things back. So the whole SEB balance thing was measured out in workshops. We went back home, did our work as architects. They did their work as material consultants or energy consultants. We came back, compromised, and went back home again. We did that for 4 rounds. So the whole thing then goes in loop. So the easiest things first, energy supply. We went into the ground, got energy from the ground source, heat pump. No actually budget for making a new technical space because we didn't really afford more concrete. So a technical space ended up in the top floor, and of course that's really expensive area, so they needed to be very compact. So new solutions for technical spaces. Climate envelope, usually quite easy, but it's hard to make passive house standard and also provide enough daylight. Also, it's important to note that all the insulation has a really heavy number of embodied energy, so you need to also carefully measure that your R values and U values are measured at the same time as you measure your daylight and your embodied emission. Ventilation strategies with displacement air coming out. Really slow-moving air needs big spaces, needs thermal mass. Thermal mass means concrete. Concrete means really crap acoustics. Acousticians want suspended ceilings. That really collides with the ventilation energy strategy. Need to work around that. Means that we need to separate the different programs so they don't conflict in the way of noise production. We need to use all surfaces to actually do acoustics absorption. Need to make sure that what we make all these acoustic elements out of is actually recycled from plastic bottles in the end, because all the materials we came out with that has some sort of a product standard of acoustic effect was full of all sorts of things that sort of made emissions into the room, that made the fans go, that made the kilowatt hours drive. So we couldn't use anything in the end that really came out of the shelf. So the new product are actually these elements that are covering both the ceiling and the walls and still providing 40% of concrete to be exposed to keep the air quality perfect. So this is actually an internal stair seen from the architect's point of view. It's the air extract shaft seen from the ventilation strategy point of view. And it's the place where people actually move around and feel that this house is for all of them, where they can meet, seen from the user's point of view. We actually got this one registered as an innovation in the center, a staircase. Another part of the story is when you need to keep your emissions down, you need to start reuse things. These really ugly facades from the 80s, sort of half blackish character, were suddenly valuable energy sitting there. We made the contractor understand that it was actually just as easy to set up his own line and produce these doors for meeting rooms based on these elements rather than buying them off the market. It actually turned out both to be cost efficient and of course you could set the embodied energy to 0. How can you make a black facade out of something which is maintenance free for about 60 to 90 years and not out of steel, aluminum or glass? That was a bit of a trick. So we found a Japanese technique of how you can burn wood and then you can kill all the bacteria and the wood will stay black forever. Unfortunately, we did lack some of the Japanese talent of treatment of some sort of oil. So we do have a little struggle with them turning a little more brown, but we will practice. Anyway, we set up a whole line for burning these, of course, not with gas. And they turned out black. Municipality was happy, steel box, still black. The park was protected. We even made a little more comfort for the starlings who are sitting up there in the little white box and got some BREEAM points for that. Summary is the embodied energy from materials and construction and transport measured down to 13.3 kilowatt hours, and delivered energy for operation is 19.7. And the important thing and the important message is that for a new building, this is actually then a higher number for embodied energy due to the fact that concrete and steel was not even counted for since this is a retrofit. So it's a pretty scary number. Oops. So I'll now, with all this background, we just apply the same thing for the next project, which is a residential single-family house. Apart from the fact that when you go into a single-family house, there's a different interpretation of comfort. So the whole discussion of comfort became a discussion on culture and climate and habits. What do Norwegians really want out of their super green home? And it turned out that comfort is actually then not about air quality in the same way as an office. It's about being allowed to be outside in the shoulder seasons, to have fireplace, to have shelter, to have weather protection, to create rooms which has this sort of indoor-outdoor connection, to have daylight, to have spacious rooms, And we applied all the techniques of doing reuse. We needed some thermal mass. We didn't afford that on our roof. We found a barn that was going to go down anyway. We took the bricks, put them up, 0 emission. Ventilation for a bedroom, you can actually take out, if you have the right materials in the room, you have a right air volume, and actually quite a cool space. Even the swimming pool is actually reused out of an old container with natural stone as the foundation. And also, I think it's an important message when you do these measurements all the way down to life cycle and changing of components, and you do have help from people who really know about different EPDs and products, you can see you need to compare your PV systems and be critical about all the technology that you add in. Just an example showing that different kinds of sun power or sun PV products, you can see the emission numbers in the mid column there is radically different, whether they're produced on renewable energy or if they're produced on coal in China. You also need to look at how many times you need to change your components within the life cycle. So it's not a big sort of hallelujah for all the technology. It's really more a critical, you need to be critical to all your components and also the technology. You need to look how many times do I need to change that component before I can really know how efficient is it really. So as you can see, when you sum up all the emissions from this residential home, if you really want to pay back every single kilowatt hour in such a small house, you end up with 220 square meters of housing and 120 square meters of PV. It's more a state-of-the-art example of how you can actually go all the way to a plus energy house, but look at the column for the PV system, it's quite high. We also need to work a lot with foundations to get out of concrete to at all be able to do this. So basic numbers are 202 square meters of housing. We came down, we had the target was actually, it's got to be less than 6 kilos of CO2 per square meter over the life cycle, which is quite ambitious, but still we think we should go down to half of that for the next time. We did achieve the indoor-outdoor connection. I think that's probably been the biggest success of this house, is that it's got these sort of different rooms and different connections, different materials that's more familiar to people than maybe what we've seen in the passive houses that's been more focused to the thickness of the wall. And just one word in the end is I've been several times asked to say something about that process in a diagram. Can you please make a circle or something that's explaining the diagram of how the architect's role is new? And I think this is the far I can get in making a diagram. And it's a lot of people and it's a lot of enthusiasm. And as long as they know their goal, like these birds, you can feel sure that they will actually end up in the same place. You just don't really know if they're doing it the same way as you're doing it. But they do actually point at the architect and look at the architect, hoping for you to be the one to bring them all together and stick to that goal. Thank you for the attention.